our two recently completed impact evaluations that we're going to highlight. The first is by Kendra Walker and co-authors. Kendra, I'll turn it over to you. And just as a note for everyone, please feel free to put questions along the way while Kendra talks directly into the chat. And then we'll take those and a Q&A at the end of Kendra's talk and then turn to our second presentation. So Kendra, go ahead and take it away.
Thank you. Is my screen showing right?
Looks
sorry,
to me.
You can see the slides? Okay, sorry about
great.
that. Okay, thank you. Yes, I am Kendra Walker from University of California, Santa Barbara, and I am presenting this work on behalf of Kelsey Jack and her collaborators, who completed a randomized control trial a few years ago to assess whether payments for ecosystem services can reduce crop residue burning in India. I am a remote sensing specialist and joined the project after the RCT was completed to try to combine the ground data with remote sensing data for more informative results. So since this is in the completed projects section, I will give you a quick overview of the RCT itself, and then I will talk about the remote sensing component, all within less than 12 minutes. So this is a speed version of the report. So the context of this project is crop residue burning, which is a major problem worldwide, but especially in Southeast Asia, where it contributes to substantial environmental and health problems. New Delhi is the world's most polluted city, and at peak periods, residue burning is estimated to cause about 30% of the pollution in New Delhi. So based on that number and similar numbers in other cities, we can attribute more than 1 million deaths per year and a 5-year reduction in life expectancy to crop burning. This figure from Jetpa et al. Is just showing the direct correlation between fire counts in red and increased rice production, which is shown by output in blue and also by NDVI during rice season, which is in green. So farmers are producing more, which is great from a development point of view, but this intensification leads to disproportionately more burning, which is very negative. Governments are trying to mitigate the problem in an effort to reduce crop burning. Residue burning was made illegal in Punjab since 2015, but compliance and enforcement is very low. In 2017, the government of India allocated funds to Punjab and Haryana to subsidize equipment purchases to manage stubble without burning it. But renting equipment still costs quite a bit, and burning is still the cheapest option for the farmer. This is where the RCT comes into play. Our PIs, through a partnership with JPAL and through collaboration with the government of Punjab, designed and conducted this RCT to test whether paying farmers not to burn would be more effective. They tested not only whether paying farmers would have an effect, but also whether the timing of that payment would have an effect. So there were 4 different treatment arms and 1 control spread across 171 villages, occupying an area around 5,000 square kilometers. This RCT was designed with a lot of great detail. I am skipping over most of that and just mentioning what is relevant to the remote sensing component here. So ground-based monitoring was done during the RCT to determine whether a field was burned or not during the season. But remote sensing is still very useful to the project, both because it can make scale-ups more feasible, but also because it is very difficult to assess the outcome in control fields with ground monitoring alone. So treatment farmers needed to call a monitor to show that they had managed their stubble without burning in order to get their payment or the rest of their payment if they had gotten some up front. So we have high confidence that the no burn labels are coming that are coming from that group. But, oh, there was also random spot checks for all the groups. So where signs of burning were found, we also have confident burn labels. But because the spot checks were random and sporadic, not finding signs of burning does not mean that the farmer never burned. So we do not have confident no burn labels for the control farmers or for treatment farmers who did not call for monitoring. And since signs of burning are very short-lived, one would have to monitor all fields probably about every week to have such labels. And this is simply not feasible on the ground. So this is where remote sensing data can be very helpful. We used imagery from both PlanetScope and Sentinel-2 to detect burning. A location is seen about every 2 days in PlanetScope and about every 7 days in Sentinel-2. And the observation frequency is very important with burn monitoring because the signal is very short-lived. As you can see here, this plot got burned on November 4th. So the second image from the left, it's burned. And by November 8th or 9th at the end here, the evidence is almost gone. You can also see this plot in the middle image next to the highlighted plot got burned around November 6th. It got burned on November 6th. You can see that in the PlanetScope imagery. There's no corresponding image in Sentinel, so it gets missed. And by November 9th, so 3 days later, it's pretty hard to tell that that got burned, at least by our eye alone. In general burn detection tasks, it is fairly easy to detect burned vegetation from unburned vegetation for weeks or even months after. This figure is just showing that the spectral signature of pre and post-burn fields is very different with many different indices, many that aren't even shown here. You can see, you get a high M value, separability. It's above 1, even 2 weeks out for all of these indices, and it's close to 2, even 2 weeks out for NIR, which is really good separability. But again, this is basically vegetation versus no vegetation. In the case of burning vegetation, our task is much harder because we aren't actually interested in the change in vegetation. Obviously, vegetation changes in a field around harvest time. And what we want to separate is bare fields that are burned from bare fields that are tilled. And that is a much more difficult task. Here, the black markers are the burned fields that we observed an exact burn date for in the satellite imagery. So that's the 0 point on these graphs. So this is looking at NIR band here, but it's similar for other bands and indices. There is a drastic change between pre and post burn. But when we compare these fields with the fields in our study that did not get burned, which are the green markers, you can see that the difference is much more subtle. In most of the days following burning, in this red box, the separability is good for the first few days, but then it diminishes quickly and is gone by 10 days. With PlanetScope here on the right, the separability is not as strong as with Sentinel-2 because there is more noise between the images. And I should mention for any Planet people here that we are using the product that is harmonized to Sentinel-2, and we're still seeing quite a bit of noise between images. So we get better separability with Sentinel-2, but we have many fewer observations with Sentinel-2. So our model uses both data sets. We developed a random forest model to predict whether each unlabeled field was burned at any point during the season. In the interest of time, I'm not going to discuss the details of that model here, just to say that we developed a broad set of features using individual bands as well as combined indices that are commonly used in burn analyses throughout the literature. And then we used differencing indices to try to pick up the change in those, as well as summary statistics for the season. And using those features, we trained a random forest model with using our 681 labeled fields in a leave one out cross-validation approach to maximize the use of our labeled data. The initial model was at the pixel level, so we aggregated to the plot level using a thresholding approach. So we selected this threshold to balance the accuracy between the no burn and the burn labels. Since with the maximized accuracy, well, because burning is more common than not burning, and 2/3 of our labels are burned, the model will perform better overall when it just overestimates burning. So we have best performance in this maximized accuracy, but you could see that the no burn accuracy is actually quite low, and it's the high burn that's very high that's compensating for that. So in our balanced accuracy, we balance these two, and we get a slightly lower overall accuracy, but we aren't overestimating burning that way. So with both of these models, when we apply them back to the RCT, we see some interesting results. Basically, paying farmers not to burn does indeed have a significant effect on whether they burn, but only when a portion of that payment is provided upfront. And beyond that conclusion of the RCT, in terms of remote sensing, we can conclude that remote sensing can help in the scale up of programs to make monitoring more feasible, but we need to be very aware of what we can actually observe with the resolution, in our case with the temporal resolution of the data we have. And we need to think about the imbalance created between burn labels and no burn labels, the latter of which are much more difficult to classify. And that's it. Thank you very much. And with that, I will do my best to answer any questions.
Thanks so much, Kendra. Nicole and others from Dev Global, I'll let you handle the Q&A. Again, as a reminder to everyone, please go ahead and put your questions in the chat, and we'll do our best to get those to Kendra.
Great. Hi, this is Nicole, Dev Global. So it looks like we have one question so far. Daniel Stein with ID Insights. How did the IE results for the remote sensing data differ from the IE results from the original RCT, which I guess use spot checks?
Yeah, I mean, again, the problem is that we basically realized we can't get accurate results without the remote sensing because the control group only got spot checks. They don't have real data on the no burn measure. Because you would have to monitor them regularly to do that. So I would say the results were inconclusive without the remote sensing data. Oh, there we go.
Great. Looks like Kelsey shared the paper.
Kelsey,
any other questions for Kendra? Maybe we'll give it one more minute. Okay, so I see one from Arthur. Slide. Is it possible to develop a combined balance and high current burn prediction approach?
I'm a little confused, I guess, about the question. I mean, we can combine the two by like putting a threshold between the two approaches. Is that, if that's the question, then that's entirely possible. Okay, yes, if that's the question, yes, that's entirely possible. We could do a sensitivity and and look and have the threshold be anywhere between those approaches. We found that with both those approaches, we got the same overall results. So anything in between would give a result somewhere in between that.
Okay, thank you.
Mhm.
We have another minute or two if anybody else has a question.
Kendra, I'm going to use the host prerogative and ask you a question. So if we were to think about applying this to a slightly different context, what do you think are the drivers of the particular geographic context that you were looking at that might have made this more successful or less successful? Such that if we were to move over to a, whether it's Pakistan or another part of South Asia or even somewhere else, that might make this easier or harder to do?
Yeah, great question. We have done some work on crop residue burning in Pakistan as well. Geographically, I would say it's actually maybe a little easier in Pakistan because there's very clear irrigation channels around the field, which we didn't see as much in the area we're working in Punjab. A lot of it really depends on, I think, the ground support and the team that is actually collecting the initial data. And because we do need some good, strong ground data of where the fields are that we're observing. So that initial data is critical, and the team that's collecting that.
Yeah, that makes great sense. Did you have actual boundaries that were walked with GPS receivers for this?
We did. And yes, the ones in Punjab were they aligned pretty well with what we see in the imagery. Whereas in Pakistan, I think also because of those irrigation channels, they had a hard time walking an exact perimeter because of flooding issues and different issues. So yes, the perimeters were a lot harder to mine.
Okay, great. Looks like we have another question from Esteban. What remote sensing or other technical advances would you like to see to enable more precise detection of burning smoke irrespective of ground data?
Yeah, so the main one we're trying to work out right now is we need something with high temporal frequency, as I was talking about. So PlanetScope data is very good in that sense, but we still need a way to normalize the data better so there's less noise between the images, so we can pick out, because the burn signal is pretty weak and it varies the same across all the PlanetScope bands. So a normalized index doesn't do the trick. We really need to normalize the imagery very robustly, as is done with Sentinel and Landsat. If that were done, I think we could pick up burn signals automatically pretty easily.
Wonderful. Okay, so this will be the last question. We're at time. From Anthony Harris, could you do this type of an analysis for a large irrigation perimeter to estimate the total area that is burned if you did not have field boundaries? How does having the boundaries of field affect the accuracy of this method?
Yeah, I mean, if it was a large field, you could definitely do that. We're working on very small fields, which are like 1 hectare. And so the issue for us was matching the fields where the burning's happening to the farmers in the trial. But certainly you could assess burning on larger areas without that data.
Wonderful. Thank you, Kendra. I'm going to pass back to Ariel now.
Thanks so much, Kendra, for walking us through that. And thanks, Kelsey and others here for pitching in with answers. Okay, we have another really interesting case from South Asia next. Grady Colleen from UC Berkeley is going to talk to us about using satellites and phones to evaluate and promote ag technology adoption. Go ahead, Grady.
Thank you so much. Yes, I'm Grady Colleen. I'm a PhD student at the University of California, Berkeley, and I'm presenting joint work with Sean Cole, Tomoko Haryaya, and Aparna Krishna that evaluates a randomized controlled trial examining a soil nutrient program in India. So just for some brief motivation for this RCT, optimal farming practices are very sensitive to local conditions, and this is particularly true of optimal fertilizer dosage, which depends on soil nutrient levels, as well as factors such as weather and irrigation. And as a result, site-specific input application schemes have helped drive large productivity increases in developed countries. But in contrast to this, agricultural advice has historically been quite static in low-income countries in the form of blanket recommendations. But recently, governments have made an effort to begin offering more precise recommendations. And so, for instance, India has distributed over 100 million soil health cards since 2015 as part of a cornerstone agricultural policy. But there's little evidence about how effective customized fertilizer advice is in these settings. And so we conducted a study in southwestern Gujarat, India, with cotton farmers producing on plots that were smaller than 20 acres, oftentimes much smaller than this, that had been recently enrolled in a mobile phone-based agricultural advisory service to evaluate this scheme, and conducted an RCT with about an equal split between treatment and control farmers and a sample size of about 1,500 in total. There are three components of the intervention. First, we gave information on soil nutrient levels, and then second, we gave information on the recommended fertilizer usage as a function of irrigation status and the soil nutrient levels that were measured from the soil tests conducted at the beginning of the evaluation. And we provided recommendations for 3 macronutrient fertilizers and 1 micronutrient fertilizer. And then this information was delivered via soil health card and supplementary material that were redesigned via piloting ahead of time to be easier to comprehend and translated into local languages. And we have pretty strong evidence that the farmers in the sample were able to understand the information and the recommendations. And then they were complemented through push calls through mobile phones through the advisory service that emphasized the information. And we had pretty high adoption. Over 70% of the treatment farmers heard at least one call about most of the fertilizer topics. And so we evaluated this in using 2 approaches. First, via surveys. We had 3 in-person surveys and 1 phone survey in which we collected information on plot characteristics, very detailed information on fertilizer use by fertilizer type and dose, and then survey measures of crop yields and revenue from the sale of agricultural goods. And then we conducted a plot mapping exercise in conjunction with the end-line survey, because this ex ante wasn't a plan for evaluation, but based off of really promising great work in the remote sensing space, we wanted to examine the use of satellites to measure crop yields. And so we collected plot mapping during the end-line survey for the majority of the sample using dedicated GPS devices and having surveyors walk field boundaries. We view ourselves as making 3 contributions. The first is on the value of targeted soil fertility information and human-centered design, which we won't talk about today. The second is on the effectiveness of mobile phone-based agricultural extension, which again is in the paper, but we won't have time to cover today. And then the third is on a satellite yield measurement component on small loaded plots, which will be the focus of the remaining talk. And so we view the opportunity is motivated by the fact that measuring the impacts of agricultural interventions is extremely costly because of large natural variations in agricultural outcomes across space and time, which has implications for the cost effectiveness of aid and policymaking in particular, since low-cost programs that might have high benefit to cost ratios are very difficult to rigorously study. And so we think there's some degree of a distortion towards higher cost programs. And there's really promising results that satellites may offer more precise measurements than survey data. And so we wanted to examine the implications of these findings for RCTs. And so for some background, there's growing evidence that satellites can produce informative signals about crop yields in smallholder contexts. But estimating economic parameters involves somewhat unique econometric considerations. First, because of the bias variance trade-off, we know that the mean squared error minimizing estimators may not be unbiased from kind of the seminal James and Stein result, where, in other words, the measures that perform best in predictive power may lose unbiasedness. And for certain applications, such as targeting, for instance, or prediction, maximizing predictive power is the most important concern. But in the context of impact evaluations, unbiasedness is often first order. And some recent work, for instance, Proctor et al. 2023, shows that in the United States, remote sensing measures have often produced biased estimates of economic parameters in estimation. And so we view this study as making 3 contributions to the remote sensing literature on satellite yield measurement. First, we show that a common practice of calibrating yield prediction models with OLS is likely to produce biased treatment effect estimates. In particular, we estimate that OLS calibrated yield predictions would underestimate true treatment effects by over 50% in our sample. And we propose the use of two-stage least squares calibration as an alternative to recover unbiased parameter estimates. Second, we examine how switching from farm-reported to satellite yield measurement affects statistical power and the sample sizes needed to detect effects of programs. The implications for power depend a lot on how we calibrate the model. With OLS calibration, we get a very optimistic takeaway that we could reduce the sample size needed by over 70% to detect the same effect. But with two-stage least squares calibration, the conclusion actually flips, and we think we'd need a slightly larger sample size in order to detect an effect. And then third, we provide a code base to kind of automate some of these practices to make it a little bit easier and less time consuming for researchers that wish to measure crop yields with satellites. To briefly describe our methodology for the yield measurement, we download Sentinel-2 products and mask out clouds using the included cloud mask, then calculate a red-edged NDVI from the imagery, which was the best performing vegetation index that we tested. We take the median value of the pixels contained in each plot's boundaries, and then take the maximum across all of the observations in a season for a plot. I'd note that we're aware that including other statistics or time series of readings can often kind of reduce mean squared error, but we don't have instruments to separately identify each of these parameters. So as I'll discuss in a second, we think that this is kind of an application of the bias variance trade-off, where we need a smaller dimension input into the measurement in order to get unbiased parameter estimates. Here's an example of the plot, and you can see that the plot maps appear to align with the imagery pretty well. Okay, so a common approach, I'd note, including in a previous version of our paper, and so we definitely don't mean that this is a criticism of any other work, for converting satellite vegetation index values into yield predictions is to estimate a least squares fit of a model of your ground truth yield as a function of your vegetation index value and noise. And then to use that OLS estimated parameters to predict yield hat, and then use the predictions of yield to estimate the equation of interest. So yield is a function of treatment, where TI is the treatment variable, and beta naught would be that the treatment effect is the parameter that we're trying to estimate. We think there are 2 sources of bias that are likely to emerge from calibrating the model with ordinary least squares. First, the relationship between yield and NDVI is not invariant to rewriting this transformation, as NDVI is a function of yield and noise. Because from reverse regression results, we know that this would be attenuated towards 0. And then second, if there's any measurement error in the vegetation index, for instance, from atmospheric interference or pixels from neighboring plots or trees, then the estimate of B will be biased towards 0 again. And so then if we consider writing NDVI as a function of treatment, then one can show that estimating treatment effects in terms of the actual output units of interest, so that's like our kilogram per hectare, for instance, of crop units, using the satellite predicted data produces a point estimate that is beta hat is gamma 1 hat times B hat. That's essentially just saying the treatment effect on NDVI times the conversion factor of NDVI to yields. And the implication is that if B hat is underestimated in magnitude, then our estimate of beta hat will also be attenuated, and so it will be underestimated. And so To get around this, we leveraged the fact that an instrument can solve problems of measurement error. And so we proposed calibrating the model with two-stage least squares, where in our case, we instrument for NDVI using the sowing date and rainfall over the season. And this seems to perform well, both in terms of instrument strength and tests of the exclusion restriction. And we get an IV estimate of the slope on REN on NDVI. So that would be B in the prior notation. That's 2.5 times larger than OLS estimate and is statistically significant. And so the implication is that if we were estimating treatment effects using the OLS calibrated predictions, then we'd be estimating treatment effects that were about 60% smaller, which in terms of factors such as benefit cost analysis could matter greatly in some contexts. And if we plot the satellite predictions of yield versus our ground data, we see that with the OLS predictions, the predicted yield distribution is quite compressed. But with the IV predictions, it appears to kind of closely match the ground truth data and the satellite data. And so we view this as kind of diagnostic evidence that the parameter estimates seem to be reasonable. This has large implications for standard error calculations. So these are treatment effect estimates and standard errors with farm reported data and then two-stage least squares calibrated satellite estimates and OLS calibrated satellite estimates. And we find that standard errors are much tighter with OLS estimates, but in fact, a little bit larger with the two-stage least squares calibrated estimates. And then if we turn to kind of power calculations for estimates to detect a 5% change in yields, we estimate that we need about a 12,000 sample size of about 12,000 with farm reported data. With OLS calibration, we'd conclude that we'd only need about 3,500. So dramatically smaller, but we think this is because we're just underestimating the variation in the data. And so if we switch to the two-stage least squares calibration, we think we need a slightly larger sample size to detect effects. And so just finally on discussion in the last 30 seconds or so, our takeaway from this definitely is not intended to be pessimistic for using remote sensing for yield measurement. We think that even kind of in this setting, which might be quite favorable to survey data, we'd only need a slightly larger sample size with satellites, but rather that some caution is warranted in trying to get unbiased parameter estimates, and that thinking carefully about bias as opposed to just prediction error is quite important. And then finally, I'd note that as I mentioned, the setting was potentially favorable to survey data because own consumption of cotton isn't much of an issue, unlike in the case of staple crops. And also as the quality of satellites improve over time, we'd expect satellites to perform even better. So thank you very much, and looking forward to questions.
Yeah, thanks so much, Grady. Really interesting stuff. Okay, go ahead, folks, pop some questions into the chat. Grady, maybe while people are doing that, maybe I could just ask you to help us think through or sort of recount what your thinking was in your, again, choice of indices and satellite data sources. I know obviously trade-offs in terms of timing, resolution, performance, all that stuff.
Yeah, absolutely. For satellite data sources, one of our goals was just to provide kind of free and open source code that could be available to any researchers to kind of immediately produce the indices to reduce the costs of using it. And so we think that there are huge benefits potentially to using, for instance, PlanetScope imagery and art against it. And so it was largely motivated by kind of the effort to provide tools for a first pass on using the methods. It could be kind of entirely automated without having to get funding or set up accounts. In terms of the indices, we tried a few, and the RENDVI essentially just had like the best predictive power. And so not really much of a conceptual reason so much as just data driven.
Yeah, thanks so much. And maybe just in the interest of fairness, since I asked Kendra about thinking about external validity and how this approach might work differently elsewhere, and you kind of threw out a teaser in the last slide about maybe this is a context that's more favorable to farmer reports. Could you kind of think through the same thing, we're taking it to elsewhere in South Asia or beyond?
Yeah, absolutely. So we think that the the finding that there can be kind of significant bias if the satellite measurements are calibrated via OLS is probably generalizable because of factors like kind of atmospheric interference or observing other plot boundaries, which we think would be true in other contexts as well. In terms of like the exact power implications, both since kind of farmers generally actually weigh and then sell most of their cotton, they have like pretty good ideas of how much they produced, and then they're not consuming it. And so we think that that's likely to paint a more favorable picture of survey yields in this setting. Whereas in a lot of other ones, we'd expect that those issues of measurement error in the survey measures are probably larger. And so satellites would look more appealing.
Okay, great. Looks like Kumar has a question. Can you suggest any other ground parameters that can help to improve yield predictions?
Yeah. So I guess just like very quickly, our choice of the sowing data or the sowing date and rainfall was motivated, in fact, by using kind of we can get rainfall data from like we used the global precipitation measurement satellite constellation, and so you don't need to collect additional ground data for it. And then sowing data is often available, and so we think that those are pretty generalizable. I think like kind of in terms of instruments that could improve the model, anything that you'd think is likely to affect yields, since anything that's affecting yields is likely to kind of only enter through, or is likely to be correlated with both NDVI and yields through that actual relationship as opposed to just noise. And so I think like a good example would be like if you have detailed irrigation variables or kind of information about practices that you think are predictive of yields, but not what you're trying to evaluate. I think those could all kind of inform that relationship better and also serve as useful controls.
Okay, thanks, Grady. Looks like Andrew has a question. So apart from yields, what other covariates were measured?
Yeah, so we had like kind of detailed plot characteristics. We didn't have inputs outside of fertilizer, and so we had extremely detailed data on like fertilizer application by time, dose, amounts, and then the labor inputs for fertilizer use. And then like farm reported measures of plot areas. Unfortunately, we didn't have other covariates such as like pesticide or insecticide use or other inputs that may drive inputs. And so we have a partial picture that's really detailed in soil nutrient use, but less detailed in some of the other inputs.
Great. Well, thanks so much, Grady. Really appreciate the talk and some really interesting hot off the presses results. So really lots of food for thought. All right, everyone. I think we're going to just take a 5-minute bio break, give you all a chance to stretch a little bit and start our next panel right at the top of the hour in 5 minutes. So see you in just a minute.